So today we went through elastic collisions, and an elastic head-on collision, such as the one shown in this diagram, both momentum and kinetic energy is conserved. That means that our momentum equation, 6.10, and our kinetic energy equation, 6.11, both hold for those two masses and their velocities, both initial and final. Now, if we go through a little bit of algebra, then we can show that these equations reduce down to something even simpler, which is just in terms of velocity. What that's actually saying is that the relative velocity before a collision is the same as negative of the relative velocity after a collision. So v1i minus v2i is equal to minus of v1f minus v2f. Basically, your object is going to collide and then go in the opposite direction. And the other object, mass 2, collides and goes in the opposite direction. So that if the masses were equal, then they might just exchange velocities, which is what this example down the bottom gives. Because the masses are equal, they exchange velocities. What we did as an exercise in class was when the masses were not equal. So I'm just going to go through this exercise again so that you can see exactly how to do it. So we aren't actually given the masses, but that's okay because they will actually reduce. What we've got is mass 1 is equal to m. So I'm just going to apply it to that. And mass 2 is equal to half of m. I'm just using m as our mass. So our initial velocity of mass 1 is plus 30 centimeters per second. And our initial velocity of mass 2 is minus 20 centimeters per second. So if we put these into the momentum equation, then we have mass times the initial velocity of 1 plus mass times velocity 2 on 2 there equal to mass of velocity final of 1 plus m on 2 of velocity final of the second object. So if we divide through by mass, we can eliminate this. So we end up with just v1i, initial velocity of the first object, plus half the initial velocity of the second object is equal to initial velocity of the final velocity of the first object plus half the final velocity of the second object. We actually have values for most of this, so let's put them in. 30 plus minus 20 on 2 is equal to v1f plus v2f on 2. So minus 20 on 2 is the same as minus 10. 30 minus 10 gives you 20 is equal to v1f plus v2f on 2. So what I'm going to do is rearrange this. Let's put 40 minus v1f, actually we're going to put 2 times v1f is equal to v2f and call that equation 1. That equation is going to be used to be able to substitute into our kinetic energy equation. So let's start with kinetic energy. Now we could do this the long way by putting in half mv squared plus half mv squared equals half mv of the final velocity squared plus that sort of stuff. Well, we're actually going to use that kinetic energy equation that we were shown before, which is our initial velocity of the first object minus the initial velocity of the second object is equal to negative of the final velocity of the first object minus the final velocity of the second object. And we have numbers again for this, so 30 minus 20 is equal to, we arrange this so it's a little nicer, v2f minus v1f. This means that we have 50 is equal to v2f minus v1f. I'm going to call that equation 2, and now I'm going to substitute equation 1 into equation 2. So we just want to put in v2f. So 50 is equal to 40 minus 2 v1f minus v1f. So rearranging this, we get 50 minus 40, so that's 10, is equal to minus 3 v1f. So v1f is equal to minus 10 on 3, which is about 3.33 centimeters per second. Now you notice that I haven't converted this into meters per second because all of our units are in centimeters per second and our masses were not known, I've left everything in centimetres per second, which means it's just slightly easier. So now we know this one. Let's substitute back into any of those equations. Let's say number 2. So 50 is equal to V2F minus 10 on 3. Or actually, minus, make sure you get your negatives right, minus 10 on 3. So V2F is equal to 50 minus 10 on 3, which is about 46.7, well, 6666 repairing, centimetres per second. Those are our answers. So that means that our initial ball, which was going initially at 30 centimetres per second in that direction, has now turned around and gone back at about 3.33 centimetres per second. And our ball 2, which was initially going at 20 centimetres per second, afterwards has turned around and gone back at 46.7 centimetres per second. And you think, well, how can this one be going faster than the other one? But this one is half the mass. So the momentum is the same, but it's turned around because it's half the mass and it's actually gained velocity to keep that momentum consistent.